This is 6.2.5.3. We're given the following difference equation, and we're asked to find the frequency response, and we're asked to find the output yn given this xn, which is 0.8 n un, a decaying exponential. Now, actually, when I did this question, the whole calculation and computation were done using j omega in the discrete time Fourier transform. But actually, I'd rather you do it in the z transform. Let's recap what we will do in the z transform. For the z transform, yn minus 0.5, yn minus 1 is converted to z transform through this step. What we do is that yn becomes yz, 0.5 yn minus 1 becomes 0.5 z minus 1 yz, xn becomes xz, and then we manipulate the equation such that we get yz on one side and xz on the other. We then get hz, the transfer function, which is yz over xz, is nothing but 1 over 1.0.5 z minus 1. At this point, if we like to work on negative power of z, we get this expression. If we like to work on positive power of z, we will get this expression simply by multiplying top and bottom by positive powers of multiplying by z on the top and bottom, which is unity. Now, then to get to discrete time Fourier transform, what we need to do is that if the region of convergence include the unit circle, then what we can then do is that simply we will replace z by ej omega, because that is what the definition of discrete time Fourier transform, and simply we'll replace z by ej omega, so the minus comes out, which is here, and the rest being the same. If you prefer to work in positive powers of z, then z is ej omega over ej omega minus 0.5, and that is h of z. So this is where it is. So it is easier actually to work in the whole grand scheme of things using the z transform, and simply first check whether the region of convergence include the unit circle, and if it is does, simply substitute z equals to ej omega to get the discrete time Fourier transform. Similarly, we use a lookup table for xn 0.8 n un. The lookup table for this expression is z over z minus 0.8. The region of convergence is absolute value of z is greater than 0.8, implying that it also includes a unit circle, and implying that we can convert this into the z transform. So finally, to get yz, it is simply yz is equals to hz times xz. And you realize again this trick, it is that to do the partial fraction expansion, we are going to do yz over z equals to 1 over z hz xz. And when we do that, then we'll perform the partial fraction, and then we'll move the z back up again so that we have a lookup table for the inverse z transform, and this is the answer. So you guys can go ahead and check that this is how we do it. Although I've done it in the discrete time Fourier transform, my suggestion to you is that to do it in the z transform and simply ensure that the region of convergence include the unit circle. I also then go ahead and write the code for this question. The question is 0.8 n. This is the input. The red one is showing the yn using the difference equation directly by pushing the input into the system, and the green one is the closed form. So you show that the closed form agrees with the difference equation. So this is the input, this is the difference equation, this is holding the memory of yn, and this is the closed form solution worked out by our previous method, which is here. So you'll see that I work it out in two ways, using the difference equation as well as the closed form solution. and then I show that they are the same. That's all. Thank you.